This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Today's reading by Daniel Harris. The Origin of Species by Means of Natural Selection, or the Preservation of Favored Races in the Struggle for Life. 6th London edition by Charles Darwin. Chapter number 6.
Part 2.
Difficulties of the Theory.
Everyone knows how the horns of stags become more and more branched, and the plumes of some birds become more finely developed as they grow older. Professor Cope states that the teeth of certain lizards change much in shape with the advancing years. With crustaceans, not only many trivial, but some important parts assume a new character, as recorded by Fritz Müller after maturity. In all such cases, and many could be given, if the age for reproduction were retarded, the character of the species, at least in its adult state, would be modified. Nor is it improbable that the previous and earlier stages of development would in some cases be hurried through and finally lost. Whether species have often or ever been modified through this comparatively sudden mode of transition, I can form no opinion, but if this has occurred, it is probable that the differences between the young and the mature, and between the mature and the old, were primordially acquired by graduated steps. Special difficulties of the theory of natural selection. Although we must be extremely cautious in concluding that any organ could not have been produced by successive small transitional gradations, yet undoubtedly serious cases of difficulty occur. One of the most serious is that of neuter insects, which are often differently constructed from either the males or fertile females, but this case will be treated of in the next chapter. The electric organs of fishes offer another case of special difficulty, for it is impossible to conceive by what steps these wondrous organs have been produced. But this is not surprising, for we do not even know of what use they are. In the gymnotus and torpedo, they no doubt serve as powerful means of defense, and perhaps for securing prey. Yet in the ray, as observed by Matteucci, an analogous organ in the tail manifests but little electricity, even when the animal is greatly irritated, so that it can hardly be of any use for the above purposes. Moreover, in the ray, besides the organ just referred to, there is, as Dr. R. MacDonald has shown, another organ near the head, not known to be electrical, but which appears to be the real homologue of the electric battery in the torpedo. It is generally admitted that there exists between these organs and ordinary muscle a close analogy, an intimate structure, in the distribution of the nerves, and in the manner in which they are acted on by various reagents. It should also be especially observed that muscular contraction is accompanied by an electrical discharge, and, as Dr. Radcliffe insists, in the electrical apparatus of the torpedo during rest, there would seem to be a charge in every respect like that which is met with in muscle and nerve during the rest, and the discharge of the torpedo, instead of being peculiar, may be only another form of the discharge which tends upon the action of muscle and motor nerve. Beyond this, we cannot at present go in the way of explanation, but as we know so little about the uses of these organs, and as we know nothing about the habits and structure of the progenitors of the existing electric fishes, it would be extremely bold to maintain that no serviceable transitions are possible by which these organs might have been gradually developed. These organs appear at first to offer another and far more serious difficulty, for they occur in about a dozen kinds of fish, of which several are widely remote in their affinities. When the same organ is found in several members of the same class, especially if in members having very different habits of life, we may generally attribute its presence to inheritance from a common ancestor, and its absence in some of the members to loss through disuse or natural selection. So that, If the electric organs had been inherited from some one ancient progenitor, we might have expected that all electric fishes would have been specially related to each other, but this is far from the case. Nor does geology at all lead to the belief that most fishes formerly possessed electric organs, which their modified descendants have now lost. But when we look at the subject more closely, we find in the several fishes provided with electric organs that they are situated in different parts of the body, that they differ in construction, as in the arrangement of plates, and, according to Piscini, in the process or means by which the electricity is excited, and lastly, in being supplied with nerves proceeding from different sources, and this is perhaps the most important of all the differences. Hence, in the several fishes furnished with electric organs, these cannot be considered as homologous, but only as analogous in function. Consequently, there is no reason to suppose that they have been inherited from a common progenitor, for had this been the case, they would have closely resembled each other in all respects. Thus the difficulty of an organ, apparently the same, arising in several remotely allied species, disappears, leaving only the lesser, yet still great difficulty, namely, by which graduated steps these organs have been developed in each separate groups of fishes. The luminous organs which occur in a few insects, belonging to widely different families, and which are situated in different parts of the body, offer, under our present state of ignorance, a difficulty almost exactly parallel with that of electric organs. Other similar cases could be given. For instance, in plants, the very curious contrivance of a mass of pollen grains, borne on a footstalk with an adhesive gland, is apparently the same in Orchis and Asclepias, genera almost as remote as is possible among flowering plants. But here again the parts are not homologous. In all cases of beings, far removed from each other in the scale of organization, which are furnished with similar and peculiar organs, it will be found that although the general appearance and function of the organs may be the same, yet fundamental differences between them can always be detected. For instance, the eyes of cephalopods, or cuttlefish, and of vertebrate animals appear wonderfully alike, and in such widely sundered groups no part of this resemblance can be due to inheritance from a common progenitor. Mr. Mivart has advanced this case as one of special difficulty, but I am unable to see the force of his argument. An organ for vision must be formed of transparent tissue, and must include some sort of lens for throwing an image at the back of a darkened chamber. Beyond this superficial resemblance, there is hardly any real similarity between the eyes of cuttlefish and vertebrates, as may be seen by consulting Henson's admirable memoir on these organs in the Cephalopoda. It is impossible for me to enter here on details, but I may specify a few of the points of difference. The crystalline lens in the higher cuttlefish consists of two parts, placed one behind the other like two lenses, both having a very different structure and disposition to what occurs in the vertebrata. The retina is wholly different, with an actual inversion of the elemental parts, and with a large nervous ganglion included within the membranes of the eye. The relations of the muscles are as different as it is possible to conceive, and so in other points. Hence it is not a little difficult to decide how far even the same terms ought to be employed in describing the eyes of the Cephalopoda and the vertebrata. It is, of course, open to anyone to deny that the eye in either case could have been developed through the natural selection of successive slight variations. But if this be admitted in the one case, it is clearly possible in the other, and fundamental differences of structure in the visual organs of two groups might have been anticipated in accordance with this view of their manner of formation. As two men have sometimes independently hit on the same invention, so in the several foregoing cases it appears that natural selection, working for the good of each being, and taking advantage of all favorable variations, has produced similar organs, as far as function is concerned, in distinct organic beings, which owe none of their structure in common to inheritance from a common progenitor. Fritz Müller, in order to test the conclusions arrived at in this volume, has followed out with much care a nearly similar line of argument. Several families of crustaceans include a few species possessing an air-breathing apparatus and fitted to live out of the water. In two of these families, which are more especially examined by Muller and which are nearly related to each other, the species agree most closely in all important characters, namely in their sense organs, circulating systems, in the position of the tufts of hair within their complex stomachs, and lastly, in the whole structure of the water-breathing branchiae, even to the microscopical hooks by which they are cleansed. Hence it might have been expected that in the few species belonging to both families which live on the land, the equally important air-breathing apparatus would have been the same, for why should this one apparatus, given for the same purpose, have been made to differ, while all the other important organs were closely similar, or rather identical? Fritz Muller argues that this close similarity in so many points of structure must, in accordance with the views advanced by me, be accounted for by inheritance from a common progenitor. But as the vast majority of the species in the above two families, as well as with most other crustaceans, are aquatic in their habits, it is improbable in the highest degree that their common progenitor should have been adapted for breathing air. Muller has thus led carefully to examine the apparatus in the air-breathing species, and he found it to differ in several important points, as in the position of the orifices, in the manner in which they are opened and closed, and in some accessory details. Now such differences are intelligible, and might even have been expected, on the supposition that species belonging to distinct families had slowly become adapted to live more and more out of water, and to breathe the air. For these species, from belonging to distinct families, would have differed to a certain extent, and in accordance with the principle that the nature of each variation depends on two factors, viz., the nature of the organism and that of the surrounding conditions, their variability assuredly would not have been exactly the same. Consequently, natural selection would have had different materials or variations to work on in order to arrive at the same functional result, and the structures thus acquired would almost necessarily have differed. On the hypothesis of several acts of creation, the whole case remains unintelligible. This line of argument seems to have had great weight in leading Fritz Muller to accept the views maintained by me in this volume. Another distinguished zoologist, the late Professor Clapauder, has argued in the same manner and has arrived at the same result. He shows that there are parasitic mites, Acardinae, belonging to distinct subfamilies and families which are furnished with hair claspers. These organs must have been independently developed, as they could not have been inherited from a common progenitor, and in the several groups they are formed by the modification of the forelegs, of the hind legs, of the maxillae or lips, and of appendages on the underside of the hind part of the body. In the foregoing cases, we see the same end gained and the same function performed in beings not at all or only remotely allied, by organs in appearance, though not in development, closely similar. On the other hand, it is a common rule throughout nature that the same end should be gained, even sometimes in the case of closely related beings, by the most diversified means. How differently constructed is the feathered wing of a bird and the membrane-covered wing of a bat, and still more so the four wings of a butterfly, the two wings of a fly, and the two wings with the elytra of the beetle. Bivalve shells are made to open and shut, but on what a number of patterns is the hinge constructed, from the long row of neatly interlocking teeth in a nucula to the simple ligament of a muscle. Seeds are disseminated by their minuteness, by their capsule being converted into a light balloon-like envelope, by being embedded in pulp or flesh, formed of the most diverse parts, and rendered nutritious as well as conspicuously colored, so as to attract and be devoured by birds, by having hooks and grapples of many kinds and serrated awns, so as to adhere to the fur of quadrupeds, and by being furnished with wings and plumes, as different in shape as they are elegant in structure, so as to be wafted by every breeze. I will give one other instance. For this subject of the same end being gained by the most diversified means well deserves attention. Some authors maintain that organic beings have been formed in many ways for the sake of mere variety, almost like toys in a shop, but such a view of nature is incredible. With plants having separated sexes, and with those in which, though hermaphrodites, the pollen does not spontaneously fall on the stigma, some aid is necessary for their fertilization. With several kinds this is effected by the pollen grains, which are light and incoherent, being blown by the wind through mere chance onto the stigma, and this is the simplest plan which can well be conceived. An almost equally simple, though very different plan occurs in many plants in which a symmetrical flower secretes a few drops of nectar, and is consequently visited by insects, and these carry the pollen from the anthers to the stigma. From this simple stage we may pass through an inexhaustible number of contrivances, all for the same purpose and effected in essentially the same manner, but entailing changes in every part of the flower. The nectar may be stored in variously shaped receptacles, with the stamens and pistils modified in many ways, sometimes forming trap-like contrivances, and sometimes capable of neatly adapted movements through irritability or elasticity. From such structures we may advance till we come to such a case of extraordinary adaptation as that lately described by Dr. Kruger in the Coryanthes. This orchid has part of its labellum or lower lip hollowed into a great bucket, into which drops of almost pure water continually fall from two secreting horns which stand above it, and when the bucket is half full, the water overflows by a spout on one side. The basal part of the labellum stands over the bucket, and is itself hollowed out into a sort of chamber with two lateral entrances. Within this chamber there are curious fleshy ridges. The most ingenious man, if he had not witnessed what takes place, could never have imagined what purpose all these parts serve. Dr. Kruger saw crowds of large humblebees visiting the gigantic flowers of this orchid, not in order to suck nectar, but to gnaw off the ridges within the chamber above the bucket. In doing this they frequently pushed each other into the bucket, and their wings being thus wetted they could not fly away, but were compelled to crawl out through the passage formed by the spout or overflow. Dr. Kruger thus saw a continual procession of bees crawling out of their involuntary bath. The passage is narrow, and is roofed over by the column, so that a bee, in forcing its way out, first rubs its back against the viscid stigma and then against the viscid glands of the pollen masses. The pollen masses are thus glued to the back of the bee, which first happens to crawl out through the passage of a lately expanded flower, and are thus carried away. Dr. Kruger sent me a flower in spirits of wine, with a bee which he had killed before it had quite crawled out, with a pollen mass still fastened to its back. When the bee, thus provided, flies to another flower, or to the same flower a second time, and is pushed by its comrades into the bucket, and then crawls out by the passage, the pollen mass necessarily comes first into contact with the viscid stigma, and adheres to it, and the flower is fertilized. Now at last we see the full use of every part of the flower, of the water-secreting horns of the bucket half full of water, which prevents the bees from flying away, and forces them to crawl out through the spout, and rub against the properly placed viscid pollen masses and the viscid stigma. The construction of the flower in another closely allied orchid, namely the cataseum, is widely different, though serving the same end, and is equally curious. Bees visit these flowers, like those of the Coryanthes, in order to gnaw the labellum. In doing this they inevitably touch a long, tapering, sensitive projection, or, as I have called it, the antenna. This antenna, when touched, transmits a sensation or vibration to a certain membrane which is instantly ruptured. This sets free a spring by which the pollen mass is shot forth, like an arrow, in the right direction, and adheres by its viscid extremity to the back of the bee. The pollen mass of the male plant, for the sexes are separate in this orchid, is thus carried to the flower of the female plant, where it is brought into contact with the stigma, which is viscid enough to break certain elastic threads and retain the pollen, thus effecting fertilization. How, it may be asked, in the foregoing and in innumerable other instances, can we understand the graduated scale of complexity and the multifarious means for gaining the same end? The answer, no doubt, is, as already remarked, that when two forms vary, which already differ from each other in some slight degree, the variability will not be of the same exact nature, and consequently the results obtained through natural selection for the same general purpose will not be the same. We should also bear in mind that every highly developed organism has passed through many changes, and that each modified structure tends to be inherited, so that each modification will not readily be quite lost, but may be again and again further altered. Hence, the structure of each part of each species, for whatever purpose it may serve, is the sum of many inherited changes, through which the species has passed during successive adaptations to changed habits and conditions of life. Finally, then, although in many cases it is most difficult even to conjecture by what transitions organs could have arrived at their present state, yet, considering how small the proportion of living known forms is to the extinct and unknown, I have been astonished how rarely an organ can be named towards which no transitional grade is known to lead. It is certainly true that new organs appearing as if created for some special purpose rarely or never appear in any being, as indeed is shown by that old, but somewhat exaggerated, canon in natural history of Natura non facit saltum. We meet with this admission in the writings of almost every experienced naturalist, or, as Milne Edwards has well expressed it, nature is prodigal in variety, but niggard in innovation. Why, on the theory of creation, should there be so much variety and so little real novelty? Why should all the parts and organs of many independent beings, each supposed to have been separately created for its own proper place in nature, be so commonly linked together by graduated steps? Why should not nature take a sudden leap from structure to structure? On the theory of natural selection, we can clearly understand why she should not, for natural selection acts only by taking advantage of slight successive variations. She can never take a great and sudden leap, but must advance by the short and sure, through slow steps. Organs of little apparent importance, as affected by natural selection. As natural selection acts by life and death, by the survival of the fittest, and by the destruction of the less well-fitted individuals, I have sometimes felt great difficulty in understanding the origin or formation of parts of little importance, almost as great, though of a very different kind, as in the case of the most perfect and complex organs. In the first place, we are much too ignorant in regard to the whole economy of any one organic being to say what slight modifications would be of importance or not. In a former chapter, I have given instances of very trifling characters, such as the down on fruit and the color of its flesh, the color of the skin and hair of quadrupeds, which, from being correlated with constitutional differences, or from determining the attacks of insects, might assuredly be acted on by natural selection. The tail of the giraffe looks like an artificially constructed fly flapper, and it seems at first incredible that this could have been adapted for its present purpose by successive slight modifications, each better and better fitted for so trifling an object as to drive away flies. Yet we should pause before being too positive even in this case, for we know that the distribution and existence of cattle and other animals in South America absolutely depend on their power of resisting the attacks of insects. so that individuals which could by any means defend themselves from these small enemies would be able to range into new pastures and thus gain a great advantage. It is not that the larger quadrupeds are actually destroyed, except in some rare cases, by flies, but they are incessantly harassed and their strength reduced, so that they are more subject to disease, or not so well enabled in a coming dearth to search for food, or to escape from beasts of prey. Organs now of trifling importance have probably in some cases been of high importance to an early progenitor, and, after having been slowly perfected at a former period, have been transmitted to existing species in nearly the same state, although now of very slight use. But any actually injurious deviations in their structure would of course have been checked by natural selection. Seeing how important an organ of locomotion the tail is in most aquatic animals, its general presence and use for many purposes in so many land animals, which in their lungs or modified swim bladders betray their aquatic origin, may perhaps be thus accounted for. A well-developed tail having been formed in an aquatic animal, it might subsequently come to be worked in for all sorts of purposes, as a fly flapper, an organ of prehension, or as an aid in turning, as in the case of the dog, though the aid in this latter respect must be slight, for the hare, with hardly any tail, can double still more quickly. In the second place, we may easily err in attributing importance to characters, and in believing that they have been developed through natural selection. We must by no means overlook the effects of the definite action of changed conditions of life, of so-called spontaneous variations, which seem to depend in a quite subordinate degree on the nature of the conditions, of the tendency to reversion to long-lost characters, of the complex laws of growth, such as correlation, comprehension of the pressure of one part on another, etc., and finally of sexual selection, by which characters of use to one sex are often gained and then transmitted more or less perfectly to the other sex, though of no use to the sex. But structures thus indirectly gained, although at first no advantage to a species, may subsequently have been taken advantage of by its modified descendants, under new conditions of life and newly acquired habits. If green woodpeckers alone had existed, and we did not know that there were many black and pied kinds, I dare say that we should have thought that the green color was a beautiful adaptation to conceal this tree-frequenting bird from its enemies, and consequently that it was a character of importance and had been acquired through natural selection. As it is, the color is probably in chief part due to sexual selection. A trailing palm in the Malay arpeggio climbs the loftiest trees by aid of exquisitely constructed hooks clustered around the ends of the branches, and this contrivance, no doubt, is of the highest service to the plant. But as we see nearly similar hooks on many trees which are not climbers, and which, as there is reason to believe from the distribution of the thorn-bearing species in Africa and South America, serve as a defense against browsing quadrupeds, so the spikes on the palm may at first have been developed for this object, and subsequently have been improved and taken advantage of by the plant, as it underwent further modification and became a climber. The naked skin on the head of a vulture is generally considered as a direct adaptation for wallowing in putridity, and so it may be, or may possibly be due to the direct action of putrid matter. But we should be very cautious in drawing any such inference when we see that the skin on the head of the clean-feeding male turkey is likewise naked. The sutures in the skulls of mammals have been advanced as a beautiful adaptation for aiding parturition, and no doubt they facilitate, or may be indispensable for this act. But as sutures occur in the skulls of young birds and reptiles, which have only to escape from a broken egg, we may infer that this structure has arisen from the laws of growth, and has been taken advantage of in the parturition of the higher animals. We are profoundly ignorant of the cause of each slight variation or individual difference, and we are immediately made conscious of this by reflecting on the differences between the breeds of our domesticated animals in different countries, more especially in the less civilized countries, where there has been but little methodical selection. Animals kept by savages in different countries often have to struggle for their own subsistence, and are exposed to a certain extent to natural selection, and individuals with slightly different constitutions would succeed best under different climates. With cattle, susceptibility to the attacks of flies is correlated with color, as is the liability to be poisoned by certain plants, so that even color would thus be subjected to the action of natural selection. Some observers are convinced that a damp climate affects the growth of the hair, and that with the hair the horns are correlated. Mountain breeds always differ from lowland breeds, and a mountainous country would probably affect the hind limbs from exercising them more, and possibly even the form of the pelvis. And then by the law of homologous variation, the front limbs and the head would probably be affected. The shape also of the pelvis might affect by pressure the shape of certain parts of the young in the womb. The laborious breathing necessary in high regions tends, as we have good reason to believe, to increase the size of the chest, and again correlation would come into play. The effects of lessened exercise, together with abundant food, on the whole organization is probably still more important, and this, as H. von Nathusis has lately shown in his excellent treatise, is apparently one chief cause of the great modification which the breeds of swine have undergone. But we are far too ignorant to speculate on the relative importance of the several known and unknown causes of variation, and I have made the remarks only to show that, if we are unable to account for the characteristic differences of our several domestic breeds, which nevertheless are generally admitted to have arisen through ordinary generation from one or a few parent stocks, we ought not to lay too much stress on our ignorance of the precise cause of the slight analogous differences between true species. Utilitarian doctrine, how far true? Beauty, how acquired? The foregoing remarks lead me to say a few words on the protest lately made by some naturalists against the utilitarian doctrine that every detail of structure has been produced for the good of its possessor. They believe that many structures have been created for the sake of beauty, to delight man or the Creator, but this latter point is beyond the scope of scientific discussion, or for the sake of mere variety, a few already discussed. Such doctrines, if true, would be absolutely fatal to my theory. I fully admit that many structures are now of no direct use to their possessors, and may never have been of any use to their progenitors, but this does not prove that they were formed solely for beauty or variety. No doubt the definite action of changed conditions and the various causes of modifications lately specified have all produced an effect, probably a great effect, independently of any advantage thus gained. But a still more important consideration is that the chief part of the organization of every living creature is due to inheritance, and consequently, though each being assuredly is well fitted for its place in nature, many structures have now no very close and direct relation to present habits of life. Thus, we can hardly believe that the webbed feet of the upland goose, or of the frigate bird, are of special use to these birds. We cannot believe that the similar bones in the arm of the monkey, in the foreleg of the horse, in the wing of the bat, and in the flipper of the seal, are of special use to these animals. We may safely attribute these structures to inheritance. But webbed feet, no doubt, were as useful to the progenitor of the upland goose and of the frigate bird as they now are to the most aquatic of living birds. So we may believe that the progenitor of the seal did not possess a flipper, but a foot with 5 toes fitted for walking or gasping, and we may further venture to believe that the several bones in the limbs of the monkey, horse, and bat were originally developed on the principle of utility, probably through the reduction of more numerous bones in the fin of some ancient fish-like progenitor of the whole class. It is scarcely possible to decide how much allowance ought to be made for such causes of change as the definite action of external conditions, so-called spontaneous variations, and the complex laws of growth. But with these important exceptions, we may conclude that the structure of every living creature either now is, or was formerly, of some direct or indirect use to its possessor. With respect to the belief that organic beings have been created beautiful for the delight of man, a belief which, it has been pronounced, is subversive of my whole theory, I must first remark that the sense of beauty obviously depends on the nature of the mind, irrespective of any real quality in the admired object, and that the idea of what is beautiful is not innate or unalterable. We see this, for an instance, in the men of different races admiring an entirely different standard of beauty in their women. If beautiful objects have been created solely for man's gratification, it ought to be shown that before man appeared there was less beauty on the face of the earth than since he came on the stage. Were the beautiful volute and cone shells of the Eocene epoch and the gracefully sculptured ammonite of the secondary period created that man might ages afterward admire them in his cabinet? Few objects are more beautiful than the minute siliceous cases of diamanticae. Were these created that they might be examined and admired under the higher powers of the microscope? The beauty in this latter case, and in many others, is apparently wholly due to the symmetry of growth. Flowers rank among the most beautiful productions of nature, but they have been rendered conspicuous in contrast with the green leaves, and in consequence at the same time beautiful, so that they may be easily observed by insects. I have come to this conclusion from finding it an invariable rule that when a flower is fertilized by the wind, it never has a gaily colored corolla. Several plants habitually produce two kinds of flowers, one kind open and colored so as to attract insects, the other closed, not colored, destitute of nectar, and never visited by insects. Hence we may conclude that, if insects had not been developed on the face of the earth, our plants would not have been decked with beautiful flowers, but it would have been produced only with such poor flowers as we see on our fir, oak, nut, and ash trees, on grasses, spinach, docks, and nettles, which are all fertilized through the agency of wind. A similar line of argument holds good with fruits, that a ripe strawberry or cherry is as pleasing to the eye as to the palate, that the gaily colored fruit of the spindlewood tree and the scarlet berries of the holly are beautiful objects, will be admitted by everyone. But this beauty serves merely as a guide to birds and beasts, in order that the fruit may be devoured and the matured seeds disseminated. I infer that this is the case from having as yet found no exception to the rule that seeds are always disseminated when embedded within a fruit of any kind, that is, within a fleshy or pulpy envelope, if it is to be colored of any brilliant tint, or rendered conspicuous by being white or black. On the other hand, I willingly admit that a great number of male animals, as are most gorgeous birds, some fishes, reptiles, and mammals, and a host of magnificently colored butterflies, have been rendered beautiful for beauty's sake. But this has been effected through sexual selection, that is, by the more beautiful males having been continually preferred by the females, and not for the delight of man. So it is with the music of birds. We may infer from all this that a nearly similar taste for beautiful colors and for musical sounds runs through a large part of the animal kingdom. When the female is as beautifully colored as the male, which is not rarely the case with birds and butterflies, the cause apparently lies in the colors acquired through sexual selection having been transmitted to both sexes instead of to the males alone. How the sense of beauty in its simplest form, that is, the reception of a peculiar kind of pleasure from certain colors, forms, and sounds, was first developed in the mind of man and of the lower animals, is a very obscure subject. The same sort of difficulty is presented if we inquire how it is that certain flavors and odors give pleasure and others displeasure. Habit in all these cases appears to have come to a certain extent into play, but there must be some fundamental cause in the constitution of the nervous system in each species. Natural selection cannot possibly produce any modification in a species exclusively for the good of another species, though throughout nature one species incessantly takes advantage of, and profits by, the structures of others. But natural selection can, and does, often produce structures for the direct injury of other animals, as we see in the fang of the adder, and in the ovipositor of the ichneumon, by which its eggs are deposited in the living bodies of other insects. If it could be proved that any part of the structure of any one species had been formed for the exclusive good of another species, it would annihilate my theory, for such could not have been produced through natural selection. Although many statements may be found in works on natural history to this effect, I cannot find even one which seems to me of any weight. It is admitted that the rattlesnake has a poison fang for its own defense and for the destruction of its prey, but some authors suppose that at the same time it is furnished with a rattle for its own injury, namely, to warn its prey. I would almost as soon believe that the cat curls the end of its tail when preparing to spring in order to warn the doomed mouse. It is a much more probable view that the rattlesnake uses its rattle, the cobra expands its frill, and the puff adder swells while hissing so loudly and harshly in order to alarm the many birds and beasts which are known to attack even the most venomous species. Snakes act on the same principle which makes the hen ruffle her feathers and expand her wings when a dog approaches her chickens. But I have not space here to enlarge on the many ways by which animals endeavor to frighten away their enemies. Natural selection will never produce in a being any structure more injurious than beneficial to that being, for natural selection acts solely by and for the good of each. No organ will be formed, as Paley has remarked, for the purpose of causing pain or for doing an injury to its possessor. If a fair balance be struck between the good and evil caused by each part, each will be found, on the whole, advantageous. After the lapse of time, under changing conditions of life, if any part comes to be injurious, it will be modified, or, if it be not so, the being will become extinct, as myriads have become extinct. Natural selection tends only to make each organic being as perfect as, or slightly more perfect than the other inhabitants of the same country with which it comes into competition. And we see that this is the standard of perfection attained under nature. The endemic productions of New Zealand, for instance, are perfect, one compared with another, but they are now rapidly yielding before the advancing legions of plants and animals introduced from Europe. Natural selection will not produce absolute perfection, nor do we always meet, as far as we can judge, with this high standard under nature. The correction for the aberration of light is said by Müller not to be perfect even in the most perfect organ, the human eye. Helmholtz, whose judgment no one will dispute, after describing in the strongest terms the wonderful powers of the human eye, adds these remarkable words: "That which we have discovered in the way of inexactness and imperfection in the optical machine and in the image on the retina is as nothing in comparison with the incongruities which we have just come across in the domain of the sensations. One might say that nature has taken delight in accumulating contradictions in order to remove all foundation from the theory of a pre-existing harmony between the external and internal worlds. If our reason leads us to admire with enthusiasm a multitude of inimitable contrivances in nature, this same reason tells us, though we may easily err on both sides, that some other contrivances are less perfect. Can we consider the sting of the bee as perfect, which, when used against many kinds of enemies, cannot be withdrawn, owing to the backward serratures, and thus invariably causes the death of the insect by tearing out its viscera? If we look at the sting of the bee as having existed in a remote progenitor, as a boring and serrated instrument, like that in so many members of the same great order, and that it has since been modified but not perfected for its present purpose, with the position originally adapted for some other object, such as produce galls, since intensified, we can perhaps understand how it is that the use of the sting should so often cause the insect's own death. For if, on the whole, the power of stinging be useful to the social community, it will fulfill all the requirements of natural selection, though it may cause the death of some few members. If we admire the truly wonderful power of scent by which the males of many insects find their females, we can admire the production for the single purpose of thousands of drones, which are utterly useless to the community for any other purpose, and which are ultimately slaughtered by their industrious and sterile sisters? It may be difficult, but we ought to admire the savage instinctive hatred of the queen bee, which urges her to destroy the young queens, her daughters, as soon as they are born, or to perish herself in the combat. For undoubtedly this is for the good of the community, and maternal love or maternal hatred, though the latter, fortunately, is most rare, is all the same to the inexorable principles of natural selection. If we admire the several ingenious contrivances by which orchids and many other plants are fertilized through insect agency, can we consider as equally perfect the elaboration of dense clouds of pollen by our fir trees, so that a few granules may be wafted by chance on to the ovules? Summary. The law of unity of type and of the conditions of existence embraced by the theory of natural selection. We have, in this chapter, discussed some of the difficulties and objections which may be urged against the theory. Many of them are serious, but I think that in the discussion light has been thrown on several facts, which on the belief of independent acts of creation are utterly obscure. We have seen that species at any one period are not indefinitely variable, and are not linked together by a multitude of intermediate gradations, partly because the process of natural selection is always very slow, and at any one time acts only on a few forms, and partly because the very process of natural selection implies the continual supplanting and extinction of preceding and intermediate gradations. Closely allied species, now living on a continuous area, must often have been formed when the area was not continuous, and when the conditions of life did not insensibly graduate away from one part to another. When two varieties are formed in two districts of a continuous era, an intermediate variety will often be formed, fitted for an intermediate zone, but from reasons assigned, the intermediate variety will usually exist in lesser numbers than the two forms which it connects. Consequently, the two latter, during the course of further modification, from existing in greater numbers, will have a great advantage over the less numerous intermediate variety, and will thus generally succeed in supplanting and exterminating it. We have seen in this chapter how cautious we should be in concluding that the most different habits of life could not graduate into each other, that a bat, for instance, could not have been formed by natural selection from an animal which at first only glided through air. We have seen that a species under new conditions of life may change its habits, or it may have diversified habits, with some very unlike those of its nearest congeners. Hence we can understand, bearing in mind that each organic being is trying to live wherever it can live, how it has arisen that there are upland geese with webbed feet, ground woodpeckers, diving thrushes, and petrels with the habits of auks. Although the belief that an organ so perfect as the eye could have been formed by natural selection is enough to stagger anyone, yet in the case of any organ, if we know of a long series of gradations in complexity, each good for its possessor, then under changing conditions of life there is no logical impossibility in the acquirement of any conceivable degree of perfection through natural selection. In the cases in which we know of no intermediate or transitional states, we should be extremely cautious in concluding that none can have existed, for the metamorphosis of many organs show what wonderful changes in function are at least possible. For instance, a swim bladder has apparently been converted into an air-breathing lung, the same organ having performed simultaneously very different functions, and then having been in part or in whole specialized for one function, and two distinct organs having performed at the same time the same function, the one having been perfected whilst aided by the other, must often have largely facilitated transition. We have seen that in two beings widely remote from each other in the natural scale, organs serving for the same purpose and in external appearance closely similar may have been separately and independently formed. but when such organs are closely examined, essential differences in their structure can almost always be detected, and this naturally follows from the principle of natural selection. On the other hand, the common rule throughout nature is infinite diversity of structure for gaining the same end, and this again naturally follows from the same great principle. In many cases we are far too ignorant to be enabled to assert that a part or organ is so unimportant for the welfare of a species that modifications in its structure could not have been slowly accumulated by means of natural selection. In many other cases, modifications are probably the direct result of the laws of variation or of growth, independently of any good having been thus gained. But even such structures have often, as we may feel assured, been subsequently taken advantage of, and still further modified for the good of species under new conditions of life. We may also believe that a part formerly of high importance has frequently been retained, as the tail of an aquatic animal by its terrestrial descendants, though it has become of such small importance that it could not, in its present state, have been acquired by means of natural selection. Natural selection can produce nothing in one species for the exclusive good or injury of another, though it may well produce parts, organs, and excretions highly useful or even indispensable, or highly injurious to another species, but in all cases at the same time useful to the possessor. In each well-stocked country, natural selection acts through the competition of the inhabitants, and consequently leads to success in the battle for life, only in accordance with the standard of that particular country. Hence the inhabitants of one country, generally the smaller one, often yield to the inhabitants of another and generally larger country. For in the larger country there will have existed more individuals and more diversified forms, and the competition will have been severer, and thus the standard of perfection will have been rendered higher. Natural selection will not necessarily lead to absolute perfection, nor, as far as we can judge by our limited faculties, can absolute perfection be everywhere predicated. On the theory of natural selection, we can clearly understand the full meaning of that old canon in natural history, natura non facit saltum. This canon, if we look to the present inhabitants alone of the world, is not strictly correct, but if we include all of those of past times, whether known or unknown, it must, on this theory, be strictly true. It is generally acknowledged that all organic beings have been formed on two great laws, unity of type and the conditions of existence. By unity of type is meant the fundamental agreement in structure which we see in organic beings of the same class, and which is quite independent of their habits of life. On my theory, unity of type is explained by unity of descent. The expression of conditions of existence, so often insisted on by the illustrious Cuvier, is fully embraced by the principle of natural selection. For natural selection acts by either now adapting the varying parts of each being to its organic and inorganic conditions of life, or by having adapted them during past periods of time, the adaptations being aided, in many cases, by the increased use or disuse of parts, being affected by the direct action of external conditions of life, and subjected in all cases to the several laws of growth and variation. Hence, in fact, the law of the conditions of existence is the higher law, as it includes, through the inheritance of former variations and adaptations, that of the unity of type. End of chapter 6.
Part 2.